so what? What are people going to do with all of this computing power? The thing that I think is really awesome is that when you go to like a computer science talk on the prospects of quantum information, they always use chemistry as their example of why this is going to change the world, which I think is really cool. So they always give the example of like nitrogenase. So nitrogenase is a very complex protein that fixes dinitrogen and makes ammonia. And we have an industrial process that does that same thing. We don't really understand how either system works. But if we had a quantum computer that could precisely describe this complex protein, we would have a chance of understanding it. That's kind of the logic. It's somewhat faulty logic, as we'll walk through with this example. So what molecule is this? Does anybody recognize it? It's one you all love. Yeah, it is caffeine. All right, so caffeine. So caffeine has 24 atoms. So it's pretty small molecule in the grand scheme of things. Let's go back to thinking about our orders of magnitude. An 8-ounce cup of coffee has something like 95 milligrams of caffeine, and that's about 3 times 10 to the 20th molecules of caffeine. And what we're asking to model here is not all of the molecules in a cup of coffee. It's just this one 24-atom molecule. So why is this hard? It's hard because these 24 atoms can exist in 10 to the 48th distinct quantum states. So if we want to perfectly describe it, we need the ability to represent all of these different atomic states or configurations. So this 10 to the 48th comes from the number of positions that our electrons can occupy in the ground state of this molecule. So, for example, in our hydrogen atoms, we have a 1s orbital that can hold 2 electrons. So there are two kind of quantum states that we need to consider. And in the minimal basis set that we want to consider representing this as, we're going to have 1 qubit for each quantum state. So, or 1 bit for each quantum state. So that's 10 to the 48 bits. And the question is, how many qubits would we need to hold the same amount of information? So if we kind of go to our 2 to the n logic, 2 to the 160 is 1.46 times 10 to the 48. So that would be good. That would allow us to hold everything about what this, all of the electronic states, quantum states of this molecule. Now, what's annoying to me as a chemist about this kind of analysis? Okay, so what we're saying is that we could perfectly describe the ground state of caffeine with a quantum computer that had 160 qubits. Yeah, okay, but is that useful? Not really. I mean, what we want to be able to do is understand more than just the ground state. We want to understand reactions. We want to do something useful. And we don't even, like, it's sort of more complicated than that because we need to somehow program this computer to hold that information, which is not trivial at all. So it is for sure more complicated than that.